So yeah, here we have the definition for the expectation. And the first one is for the discrete case, which is sum over all possible x, and that x follow a probability mass function, p of x. So just summation over x, x multiplied by p of x. And then for the continuous case, we have this integral here. So x multiplied by p of x, and then we take the integral with respect to the support of x. So definition for expectation for two different cases. And here we also have the variance of x. It can also express in the form of expectation and x minus mu squared. And with some expansion and then rearrangement, we can get another formula that we often use. So e of x squared minus the square of the mu, or the first moment. Yeah. So more of a definition for the expectation and variance. And for now, this is more of a FYI or a list of a very common distribution that we often use. Yeah, it will be a long list and more of a for display, so there's no need to take notes or to memorize. And I think you are also allowed to bring the cheat sheet to midterm. Yeah. So for the first one, we have this Bernoulli distribution, and the support is 0 and 1. So in the context of coin tosses. So we have 0, say, landing on tail and 1 landing on head. And then the formulation for a Bernoulli distribution is that p of x, p raised to the power of x, and then 1 minus p raised to the power of 1 minus x. So the way to read this is that the probability of landing on head, and then x serve as an indicator, 1 or 0. So you either observe that or not. And then 1 minus p is the probability of failure or landing on tail. And then 1 minus x would also serve as a indicator that you get a head or tail. Yeah. And then expectation and the variance for the Bernoulli distribution equal to p, and p multiplied by 1 minus p. And for these two, or for all the this expectation and variance for different kind of distribution, you can always use the definition here as a way to show or to check whether what the expectation or the variance is for a particular distribution. So as a practice, you can calculate this and see if it is equal to the one that I listed here. Okay. Then after a Bernoulli distribution, we have this binomial distribution. So instead of one tossing the coin for once, we can also toss the coin for n times. And this is, and then for the binomial distribution, we are basically trying to measure out of n tosses how many times we observe a x landing on head. So this is the formula. The support is ranging from 0 to n. So out of n tosses, it's possibly that you have no, you don't observe one head at all, and then you observe all coins are landing on head. And this is the formulation for the binomial distribution. So we have this very similar to the Bernoulli case, except that we have this binomial coefficient. So the unchoose x serve as a rearrangement, how many head that you can obtain out of n tosses. For example, if you have 3 heads, it can, out of 10 tosses, you can have 1/3 position that you get a head, and then the rest of them landing on tail, but you can have different rearrangement. So the binomial coefficients serve as to rearranging those those combinations. And then this part will stay the same, the probability of landing on head out of x occurrence, and then 1 minus p. Yeah.
Why do we have Bernoulli when it's just like binomial distribution with n equals 1?
I think it will be the same thing, right? If you have n equal to 1, then it will collapse to the Bernoulli case, right?
Yeah.
Oh, so what's your question?
Oh, I'm just wondering, like, why they're two separate distributions when it's like a subset of a different distribution?
I don't know the reason, but it just, yeah, I think it just, it would be easier to measure that, but I'm not sure the reason. But just, yeah.
I think it's just because Bernoulli is like a really popular one, so it's just named after like that. But
Thanks. Yeah, yeah. Feel free to stop me, or if you have any question or any comments. Yeah, thanks. Yeah, and then we have the expectation and the variance. And next we have this geometric distribution. The support is ranging all the natural number. And what we are trying to measure here is that how many occurrences that you need until your first success. So the formulation for this geometric distribution, we have 1 minus p, so the probability of failure or landing on tail, raised to the power of x minus 1. So you need x minus 1 failure until your first success. So this is what geometric distribution is trying to measure. And then we have this expectation 1 over p and the variance 1 minus p over p squared. There's only one parameter in this distribution, p. And then we also have this negative binomial distribution. And the support is also a natural number with a 0. And this is the formulation, and then with 2 parameters, so r and p. So in this case, we are trying to measure the number of trial until the rth occurrence. So in contrast to the binomial distribution, where we fix on the number of total trial, the total number of the trial. So n is fixed, and then we measure how many times we get landing on head. And in this case, we are trying to fix on, we want to get rth occurrence, say r heads. How many trials do we need? So this is what negative binomial distribution is trying to measure. So kind of the opposite of the binomial distribution. And then for the expectation, we have 2 parameters, so r over p, and then r multiplied by 1 minus p over p squared. And you can also you can always use the definition for expectation or variance with this particular form of the distribution, and then you can evaluate or to verify the expectation of the variance. And our last commonly used distribution in the discrete case is the Poisson distribution. So again, the support is a natural number with a 0, and the formulation like that with 1 parameter. It has the property that expectation equal to variance and then equal to lambda, the parameter for the Poisson distribution. Yeah. So yeah, this is just a very tedious, more of a display FYI thing. So yeah, any question or comments? Okay, then we can proceed to the continuous variable. So instead of that saying that x equal to a particular number, we usually refer a continuous random variable that fall in between a range. And then we can use integral to evaluate that. So f of x is the PDF, and then taking the integral between the range a and b with respect to x. Yeah, so we don't say x equal to a particular number anymore, because if you set a equal to a constant, so and then the integral will be evaluated to 0. And then yeah, a few commonly used continuous PDF here. So the first one is the uniform distribution, also parameterized by 2 parameter a and b. Basically, it's the range. And then, so it's 1 over b minus a. And then the expectation and the variance. Yeah. I think you probably need some trick to evaluate this variance of x. And another continuous random variable PDF is the exponential distribution. Yeah, and then the support is now continuous number So from 0 to positive infinity. Also parameterized by one lambda here. And it has the expectation, it's just 1 over lambda. And then the variance is the square of the expectation, so 1 over lambda squared. And our final, and then we also have the normal distribution. So the support is ranging from negative infinity to positive infinity. And the formulation will be like that with two parameters. So one control the mean and the other one control the variation. We also have a special case for a normal distribution, which we call standard normal distribution, particularly when mu equal to 0 and sigma squared equal to 1. It can collapse or simplify into that form. And if we are able to generate or to sample from a standard normal distribution, we can always, using this reparameterization trick, to sample or to generate another normal distribution that follow a general normal distribution with particular mu and sigma here. So yeah, as long as you can sample one from the standard normal. And I think in the computer, it also used some kind of trick to sample that. And then I think back in old days, the computer will probably use this one to generate normal distribution. And there's also a long history that how computer code are written to generate bivariate normal. And there are lots of tricks in the underlying process, besides our just using one line to call in R. And then there's lots of things going on in the backend. So basically just a long list, tedious. Yeah. Any question or comments?
Z just a Z score, right? Is it just like D score?
In this case, Z is one we sample from the standard normal. But if we have a general normal, then if you use x minus mu over sigma, then it will become a Z score. It just, yeah, in the different context. Yeah, but if you read it in the term, it will be the way that you calculate the Z score. Yeah, good question. Any other question or comments? Good. I hope I'm not, this is not too boring or too easy for you guys. Or if it is very boring, let me know, I can skip this. Okay, next we'll talk about moment generating function. So literally it's just a function that can generating moments with respect to a particular distribution. So yeah, so the moment generating function, we use the capital M to denote that. And it is a function of t. And then with respect to a random variable x. And it has the form or definition is an expectation to the exponential of tx. This e here, it's basically just a shorthand for the exponential, that exp here. And also another complaint that I often get is from the math students is that in stats we often use this log here. We referring to the natural log. So what we want or what we have is something like this. So yeah, so the log is for the natural log. Otherwise, people in the math department, they always complain what is the base for that. So this is what we are referring or what we use. Yeah.
You just use a ln.
Sorry, what?
ln.
Yeah, it just in the literature people always use log, so it's yeah, but it should be ln, yeah, but people just use l, yeah. So yeah, many people complain that it's not clear in the stats. Yeah. Okay, yeah. So that's the definition for the moment generating function. And then it also involves expectation. So now we also have two cases. So one is the summation all possible x, and the integral over the support for the particular random variable x with its corresponding PDF or PMF. And anything else? Yeah. So more of a, so far still the definition. And yeah, so we basically can, or we can use moment generating function to calculate the moments. And from the moments, we can evaluate, say, mean and the variance. And next, I'm just going to show how we can, or the reason, or the underlying reason how we can achieve that. Yeah. So yeah, so first, yeah, because we have this exponential tx, this term here. So we are first going to use Taylor expansion to rewrite this term here. So yeah, so the e of x can be expressed as sum, as a sum. And then with this x, I use the index n here from 0 to infinity. And then x raised to the power of n over n factorial. And here I just write all the terms explicitly. And then what we have seen in the moment generating function is that the e of tx. So what we need is just replace the x on the numerator to tx. And then all the other terms can be updated like this. And now we have this term rewrite as a summation. And then we can plug that into the moment generating function. And then I'm going to use this discrete case for an example. For the continuous case, all you need is just to change this summation to integral. Yeah. So what we are going to do next is to evaluate this without specifying the p of x for now. And later we have an example for a particular choice for p of x. Yeah. So once we have e of tx, exponential of tx, expressed as a summation, and we can plug in into this part here. So this is what we have here. So the moment generating function for the discrete case is the summation over all possible x, e of tx multiplied by px. And we just replace e of tx with the summation here. And then basically it's a summation over another summation, and then we can just rearranging the term. So for example, we can just multiply this p of x to 1, and then sum over all possible x. That's the first term here. And then we also have sum over all possible x, this term here multiplied by p of x, and then the same implementation for all the other terms. And then t here has nothing to do with this summation, so we can bring it outside as a constant term. Same implementation for the rest of the remaining terms. So now we have a moment generating function without explicitly specifying what distribution that we are currently talking about. So yeah, so we just use p of x to refer to any PMF for now. And the reason why we can use moment generating function to calculate the moment, or the way to use that is that we can take the first order derivative. So moment generating function is a function of t. So our derivative is also with respect to t. So now we just take the derivative of this with respect to t. So nothing on the first term, it becomes a 0. There's only one t in the numerator, and it will be like that. T squared will just be 2t, and then 3t squared. So all the remaining term will still have a t involving. And next, we let t equal to 0. We can see that it will simplify to this one here. And as we showed at the very beginning, basically this is just the expectation. So by constructing a moment generating function, and then with this kind of taking kth order derivative, or for now it's first order derivative, and then set it t equal to 0, we can get the first moment. And then in general, we can if we have a moment generating function for a particular distribution, we can take the kth order derivative with respect to t, and then let t equal to 0, then we'll have the kth moment for this particular distribution. So that's, and then by using, in this way, we can, or more of a reason why we are able to achieve this. Any question or comments? And yeah, so this is just an example for the first moment. And we can also do the same thing or for the second moment. Yeah, we take another derivative from here with respect to t again, from here. Yeah, so this one has nothing to do with t. Same thing for the second term. And this one will, the t will be removed. So we are left with this. And all the remaining terms will still have a t involving. And for now, if we let t equal to 0, and then we can simplify into this form. And this is basically the second moment, x squared multiplied by p of x. So it's the expectation of x squared. And variance can also be obtained from here. So basically it's the e of x squared minus the square of expectation. So once we have a moment generating function, first moment, second moment, we will be able to obtain the mean or the expectation and the variance. Yeah. So yeah, it's just one application that we can use for the moment generating function. Any question or if it's too boring? Or okay. Yeah, so next we will just have an example for the moment generating function. And here we are going to use exponential distribution as our example. So this is the formulation for the exponential distribution that we see earlier. And now we are going to calculate the first and the second moment, and then to evaluate the expectation and the variance. So from earlier, we see that the expectation is 1 over lambda, and the variance is 1 over lambda squared. And now it can be, those results can be obtained from using the definition of expectation and variance. But over here, we are just going to use the moment generating function and then to evaluate that, and then we are going to verify if we can get the same thing for the expectation and variance. And yeah, different from the previous example here, we didn't specify the explicit form for the p of x. And now we just we have this particular choice. This PDF here is regarding exponential distribution. Okay, so yep, start from the definition of the moment generating function. So expectation of exponential of tx, taking the integral. So the support for the exponential distribution is from 0 to infinity. And then this is the e of tx, basically this part in the parenthesis, and then multiply by f of x. So this is our choice for our particular example here. Lambda has nothing to do with dx, so we can bring it outside the integral. And then we are left with exponential negative lambda minus t multiplied by x. This might be a little bit difficult to evaluate for now, so we are going to use substitution to work on that. So we let u equal to this part without the negative sign. And rearranging the term, we have this x equal to 1 over lambda minus t multiplied by u. And then dx is just this multiplied by du. Then we can rewrite this integral here, which may be difficult to evaluate, and then we rewrite the integral with from with respect to x to with respect to u. So this is the original integral, and we rewrite this part as u, so it becomes exponential negative u. And then this dx is just 1 over lambda minus t du. And then, so this becomes a constant term, has nothing to do with x, nothing to do with u, so we can bring it outside. And yeah, also by doing this substitution, here is talking about x equal to 0 and x equal to infinity. But now when we change the integral to u, then here is talking about the lower bound and upper bound for u. So if you plug in 0 and infinity here, you will find that the lower bound and upper bound for u is also 0 to infinity. So this here is actually u equal to 0 and u equal to infinity. And then we evaluate this integral with respect to u. We will achieve this and evaluate it at the upper bound and lower bound, and then we will have lambda over lambda minus t. So yeah, so up to this point, we obtain our homogeneous function for this particular choice of PDF, or exponential distribution. Any question or comments? Okay. Yeah, so yeah, another or you can say property, or is that we can use the homogeneous function as an identity to identify a particular distribution. So whenever, if you're working with if you're working with any with a distribution, and then you find out that your the homogeneous function can be simplified into this form, then you have a very good knowledge about the distribution that you're currently working on is probably related to exponential distribution, or it is exponential distribution. So it can also use as an identity for a particular distribution. Okay, so once we have that, that's our MGF. And now we can evaluate the first and the second moment with the above implementation. So taking a derivative and then set it equal to 0. So here is the homogeneous function. We take the first order derivative with respect to t, as homogeneous function is a function of t. And then we have this, set t equal to 0. We have 1 over lambda. And this is the expectation that we see earlier in that in the list. And we can also take the second order derivative. We will have this, let t equal to 0. So we have 2 over lambda squared. And that is the second moment. And then our last step is to use the second moment minus the square of the first moment, or the expectation. And then we will have 1 over lambda squared. And that is the variance that we also see earlier for the exponential distribution. So yeah, it's just another way or application for the homogeneous function, and then to evaluate the expectation and the variance. And yeah, this is very likely to be your homework in the homework. Any question or comments? Yeah.
Why would we set like t to 0? Like what changes t to 1?
Yeah. So yeah, that's a good question. So by setting t equal to 0, we observe that we are able to collapse all the terms into this form, and then it gives us like a, say, a shortcut to this by setting t equal to 0. So that's why we want to set t equal to 0, and then to remove in this from this function here, and then we are able to get the particular kth moment after we take the derivative and set t equal to 0. Does that answer your question?
So like, do people ever use t equals 1, t equals 2?
No. I think if you set t equal to other numbers, then you will not be able to collapse or to remove all the other terms, and then to get a clean or a clear or a shortcut for this expectation. So this is the part that we want. By setting the t equal to 0, we are able to achieve this. Yeah. Good question. Any other question or comments? If not, then this is all I have for today.
You said that you'll be posting this on.
Uh, Yeah, I think.